So in this outing, this lecture, we will study the kinematics of rotational motion about fixed axis and the analogues of the translational motion with the rotational motion. What are the various attributes and comparatively the attributes that we have in the rotational motion. Now, to tell you about the rotational motion that we have, I have a rigid body, and in this rigid body I have a point C about which this point P is rotating, okay, about this Z axis. Initially at time t is equal to 0, this point was here on the circumference of the circular path that the body will follow. So at t is equal to 0, this is at p is equal to 0, and at that time the angle that makes with the x-axis, we have taken x-axis like this, y like this, and z like this, and the angle between x and y and z and x, they are all 90 degrees. This is an orthogonal coordinate system. So we find that the initially at point t is equal to 0, the point under consideration is p naught, and that makes an angle of theta naught, theta 0 with the x-axis. So x-axis is the reference axis with which the vectors make the angles. Of course, there is a uniform circular motion kind of a thing. So equal angles are traversed in equal intervals of time. At time t, this angle becomes equal to, this whole angle becomes equal to theta. So that the angle that has been traversed between the time t and t is equal to t is theta minus theta naught. And the location of the point at that time is at p. Okay? We are describing the arbitrarily chosen point where the x-axis and the y-axis and the z-axis has been shown to be at the point O, which we take the origin of the coordinates for the system. We'll make use of this figure for determining many things, but first of all I will compare the translational motion and you will compare it with the rotatory motion. So one of the thing is the displacement x, which is a vector quantity, and so is theta in radians. This is also a vector quantity. In the algebra that we developed, I have not shown it to be a vector quantity, but then the next item that we must have is the ddt of x, and that is defined as the velocity, instantaneous velocity, which is given in meter per second in the case of translatory motion, and the corresponding value is omega is equal to d theta over dt. This is radians per second. Next, we differentiate this velocity with respect to time to obtain what is known as the instantaneous acceleration associated with the body. Under motion, translatory motion, it moves from one point to another point in a straight line. Then this again can be said to be equal to d2x upon dt2 meter per second square. Similarly, on the lines, I define the angular acceleration alpha. This is also a vector. Like this is a vector, this is a vector, and this is a vector. On the same line says x is a vector, y is a vector, a is a vector. Okay. But I am not writing that vector signs over here. So I have the corresponding thing is the angular velocity, which is defined as, on the same lines, d theta over dt in radians per second. Alpha is equal to d omega over dt is equal to d2 theta upon dt2 radians per second square. Now, when we studied the translatory motion for a constant acceleration. When the acceleration is constant and the initial velocity is equal to v0, we find a relation. The final velocity at a time t is given as v0 plus at. The second equation we have, the displacement x minus x naught is equal to v0 t plus half at square. By now we remember this equation by rote. And then the third equation is v square is equal to v0 square plus 2a x minus x0, which is the total displacement which is there. We have proved these equations from the first principles, and the corresponding equations for the case of rotational motion about a fixed axis, we find that the angular velocity it is subjected to a constant angular acceleration is equal to omega naught plus alpha t on the similar lines, and like x minus x0 is theta minus theta 0 omega naught t plus half alpha t square, and omega naught square is equal to omega naught square plus 2 alpha theta minus theta naught. Remember, I told you that if I multiply this whole equation throughout by half m, then I get half mv squared, which is the final kinetic energy of the particle, half mv0 squared, which is the initial kinetic energy, and plus the ma x minus x0. Ma is the force. We'll find like it has been given over here, and then force multiplied by the displacement in the direction of the force, that gives the work done. So that is also one point. So similarly here also I can say that omega is equal to omega naught plus alpha t, theta minus theta naught, which is the angular displacement time t, is omega naught t plus half alpha t square, and omega square is equal to omega naught square plus 2 alpha theta minus theta naught. Of course, the MKS or SI units are given over here, and those units can be substituted. And one thing should be borne in mind, that in any equation, not only these equations, wherever there is a plus or minus sign, then the units of those things, the unit of this, and this whole thing will be the same. Unit of this, and this is the same. Unit of this, and this will be the same. So, bearing in mind, then the next item that we compare in two motions, translational motion and the rotatory motion, that is a concept of the mass. The mass of a body, which is the measure of inertia. According to Newton's first law, we define that mass is a measure of inertia of the body, by virtue of which it opposes the if the motion is caused to change, then there is an opposition. Kahili, I said to you when we were discussing this. So similarly, this is called the moment of inertia. The moment of inertia is an analog of mass, similar to mass. Then we had Newton's second law, which he defined as F is equal to ma. Here I have written the vector form, showing thereby that the direction of F and A will be the same, because mass is a scalar quantity, and we obtain the vector quantity by multiplying another vector quantity with a scalar. So the corresponding thing over here is tau is equal to I alpha, and I'm an idiot till I balance it by saying both sides is vector. So torque is a vector quantity, we define as torque is equal to the moment of inertia into alpha, which is the angular acceleration of the system. Similarly, while dealing with this, I told you about quantity P is equal to mv, which I called in Hindustani, I called it jhonk. Okay, so similarly, I have the angular momentum L, which is again in similar manner given by the moment of inertia multiplied by the angular velocity. If we work out the kinetic energy associated with the particle, it is equal to half mv square here, and k is equal to 1 by 2 I omega square. Remember, I derived the kinetic energy by a formula P dV, and I integrated it between the limits 0 to v, and this turned out to be equal to mv dv. So I can write it as m integral 0 to v dv, and this turned out to be equal to v square by 2. So half mv square I defined to you with the help of this integration process. So I am just giving you a quick reminder, and we return to obtain these relations, these three relations from the first principles. So we show the first equation, omega is equal to omega naught plus alpha t. We derive this equation from the first principle, and that is alpha is defined as d omega over dt and is taken as a constant for the system that we are describing. Now I am writing this d omega over dt is equal to alpha is equal to constant, or d omega will be equal to alpha into dt. Integrating, left hand side I have from omega naught to omega, d omega is equal to from 0 to t, the limits, alpha dt, alpha is the constant, I will take it out here, and then as I told you in the case of the derivation of v is equal to v0 plus at in the translatory motion, the same pattern is going to follow. In fact, omega between the limits omega naught to omega is equal to alpha into, because this is t to the power of 0, which I have just substituted for 1, and t to the power of 0 plus 1 divided by 0 plus 1, which turns out to be equal to t. And so when I apply these limits on the left hand side, I get omega minus omega naught is equal to alpha t minus 0, or I can write the final equation, the omega is equal to omega naught plus alpha t. Of course, we have to use the given boundary conditions. So again, the second equation, theta minus theta naught is equal to omega naught t plus half alpha t square, rx minus x naught is equal to v0 t plus half at square, from the basic definition of omega, and that is omega is equal to d theta over dt, or v is equal to dx over dt. Translatory motion. So I am just revising it for you. Omega is equal to d theta over dt. I write it from here, from the basic fundamental definition of omega. Here, of course, alpha is a constant like before. So I write this omega dt is equal to d theta. And of course, the value of omega we derive from the last equation, and we substitute it here. Omega is equal to omega naught plus alpha t. So I write it as omega naught plus alpha t into dt is equal to d theta. And integrating between the limits 0 and t, this term omega naught plus alpha t dt, and theta 0 to theta d theta, and escaping that one step where d theta will, integral d theta will be equal to theta, etc. So I can write omega naught, and here it is t to the power of 0. So integral of t to the power of 0 will become equal to t to the power of 1. So this turns out to be equal to omega naught t plus alpha t square between the limits 0 and t. I have just put the boundary conditions, okay, is equal to theta between the limits theta 0 and theta. I substitute those limits, and of course I write the term omega naught t plus half alpha t square minus 0 minus 0. So that turns out to be equal to 0. I have just escaped that term also, but you should understand it. This is equal to theta minus theta naught. I am just rearranging the terms, so I get theta minus theta naught is equal to omega naught t plus half alpha t square. To derive the third equation, and that is omega square is equal to omega naught square plus 2 alpha theta minus theta naught. It's easy, like we did in the case of the translational motion. I just squared this relation, and this will turn out to be on the left side omega square, on the right side omega naught square plus 2 omega naught alpha t plus alpha square t square, and when I rearrange the terms I obtain this as omega square is equal to omega naught square plus 2 alpha theta minus theta naught. So all these three relations with the help of each other can be proved, and the same will happen in a nutshell. I'll just tell you, in translation motion this velocity is equal to dx dt, so this v into dt turns out to be equal to d x, so v naught plus alpha t, at dt, because that will be a relation that will substitute here, and then ultimately what I get is x minus x naught is equal to v naught t plus half at square. So this is how these equations, the translational set of equations where a is equal to constant, the acceleration is equal to constant, and in the second one the angular acceleration is constant. Under those conditions these relations can be obtained, which describe the two motions under these compelling conditions, that constraints that a is equal to constant, the acceleration is the constant, and here the angular acceleration is constant. So we take an example, simple example, which reads: the angular speed of a motor. Here by angular speed we mean the angular velocity, that's omega. The angular speed of a motor is increased from 40 pi radians per second to 104 pi radians per second in 16 seconds. So naturally we are going to apply a torque, and which produces a uniform angular acceleration. And to produce a torque we must have a force acting in the system at a distance away from the axis of the motor. The angular speed of a motor is increased from 40 pi radians per second to 104 pi radians per second in 16 seconds. Calculate the uniform angular acceleration alpha of the system. How many revolutions the engines make engine makes, how many revolutions the engine makes during this time interval, that is 16 seconds. So it is a simple use of this equation. Omega is equal to omega naught plus alpha t, where alpha is a constant. Okay, we have written for constant, we have written the term uniform. So we use this, where omega naught is equal to 40 pi radians per second and omega is equal to 104 pi radians per second. Okay, so from this relation I can write alpha is equal to omega minus omega naught divided by the time interval t. So 104 pi minus 40 pi divided by 16, this turns out to be equal to 4 pi radians per second square. The second part, where we are asked to calculate the number of revolutions that has taken place in this time interval of 16 seconds. So here I apply the second equation, and that equation is theta minus theta naught is equal to omega naught t plus half alpha t square. Theta naught we take as equal to 0, and then we substitute these values, 40 pi into 16 plus half into 4 pi into 16 square, which is 256. So it turns out to be equal to 140 pi plus 512 pi is equal to 1152 pi radians. Now, the angle that is traversed in a single revolution is 2 pi radians. So 1152 pi divided by 2 pi will give you the number of revolutions that we have. Pi cancels pi. If I divide this by 2, I get 576 revolutions for this question. Of course, in a question like that, we can always change the values of the angular velocities, the value of the time interval, etc., and obtain the result. Okay. The next thing that we take up in the next lecture is the dynamics of rotational motion. So far as kinematics, now we are going to deal with the dynamics. Dynamics of rotational motion. Okay, in the next lecture. So, like I say, that in doing physics, the important thing is that we interact. We interact when you ask questions, and we answer. So please ask questions, subscribe to the channel, and readily in the comments section write your comments, suggestions, etc. But also if you have any queries, please ask those queries, and we meet again soon.